Hey everybody, welcome to week 14 of PS 398. So in the previous lecture, we broached the subject of incomplete information. Are there certain things about the game that some players know and other players don't? So we talked about that in simultaneous moves in the context of an extended trade war model. And then at the end of last week's lecture, I sort of hinted about where we were going to be headed by looking at an extensive form model of incomplete information, the so-called standard model about how two countries might bargain when one of them knows something that the other one doesn't. And in what might have been the worst cinematic trick of all time, I decided to leave a cliffhanger ending to last week's lecture in the hopes of just getting you excited about talking about these matters today. Now, you can use extensive form models with incomplete information for all sorts of things, and the next 2 weeks and on the final, I'm looking forward to trying to show you some cool examples of different phenomena that get modeled that way. My main goal for today is just to give you enough machinery to be able to play in that particular sandbox for the next 2 weeks plus the final. When you think about it, extensive form games of incomplete information represent a very natural stopping point for a class like this. So we take everything that we've talked about. We take rationality. Those were the days, right? We take rationality. What is it to have consistent preferences? What is it to make consistent choices? We turn rationality into social rationality by introducing the concept of a game. We talk about what collective rationality looks like, what aggregated rationality looks like in the context of Nash equilibrium. And then once we were at Nash equilibrium, which in a lot of respects is like the end of Act 1 of the class, or maybe Act 2. Boy, this class really has lacked a center, hasn't it? I'm so sorry to have put you through all this. Not that sorry. And then we took the concept of a game and the subsequent notion of collective rationality of Nash equilibrium, and then we extended it in two directions so far. We extended it by talking about time with extensive form games and repeated games, where credibility, the shadow of the future, looking down the tree, and then subsequently backward induction when possible. That style of analysis, hopefully, is one of the things that you've really gotten out of the class. And then last week we extended by talking about the role of information. And so extensive form games of incomplete information, therefore, are the culmination of those two extensions from the core concept of rationality, collective rationality, and aggregated rationality. Now it's time and information and how they play with those three basic factors that live underneath any game theoretic model. How do I take things that I can observe, which requires time, right? In order for me to be able to observe something and then condition what I do on what I observed, I need time. I need an extensive form apparatus. But what happens if I don't know everything? Does that give me an opportunity to learn? Or does this new source of uncertainty in the form of incomplete information, does that require me to make some more smushy type decisions in the form of expected utility calculations? And we're going to see the answers to all these questions is it depends on how time and information are relating to one another. And so my goal for today's lecture is actually just to show you two different ways to think about time and information, one of which involves making a decision when somebody might respond and you don't know anything about them. In other words, nature makes a choice. I don't know what nature chose, but I have to make a choice. And then you observe what nature did and what I did, and then you get to make a choice. So the standard model that I showed you at the end of last week's lecture is in that class, right? That's one where the uninformed player, state A will be the uninformed player in that model, and the uninformed player moves first. Okay? They don't have any information, and yet they have to do their best. Another important class of one-sided incomplete information models with time structure is what you might call a signaling model, where the person that has information moves first. Nature makes a decision, and then the person that observes that decision, the person that knows their own type, makes some decision. And then the uninformed player observes not the state of the world, but they get to see what happened. Right? They get to see what the informed player chose. And so they go into it with an extra data point. They get to go into it thinking to themselves, hey, would the informed player have done what I just observed them doing if they were the wrong type of that player, right? So here they've got to be thinking through. They have new data on a signal that they observe. They get to use the actions of the informed player to draw inferences about what kind of opponent they're up against. So really, all I want to do today is show you what happens if the uninformed player moves first, and what happens if the uninformed player moves second in one-sided, extensive form models of incomplete information, both of which will be about war today. I'd like the story to be relatively straightforward across the two. In the standard model that I'll show you early in the lecture, I'll be talking full-on bargaining model of war, and then as we hint at signaling, which will be an important topic next week as well, I'll try to keep things more numerical and focus more on the style of analysis that we do, because signaling models where the uninformed player moves second, there's a couple little additional details that I'll need to show you in terms of how we analyze them. Along the way, I'll be showing you basically the rudiments of what is called perfect Bayesian equilibrium, which is the current workhorse concept of equilibrium in applied political science and international relations. I'm not going to get all the way into formal definitions of this. I really just want to show you more by way of example. I assure you, this will be enough to get your heart pumping. And if you have more detailed questions about any of this, of course, feel free to let me know, as ever. But seeing as how this is something of a culmination of all the hard work you've been putting in throughout the rest of the class, I hope I don't have to motivate things too much. This should be getting ready for... I hope you're ready for the punchline, because here it comes. In the A block, we will revisit the standard model as introduced last week, and I will show you how one analyzes it via something that looks a lot like backward induction. It's really backward induction. It's just a slightly more complicated version of it. We're going to see in the standard model that the prior belief that the uninformed player has, their initial empirically motivated belief about the probability that they're up against a strong opponent, we're going to see that prior belief plays a very important role in determining whether or not there's violence in this bargaining model of war, this third bargaining model of war that we'll have looked at in this class. We saw one with issue indivisibilities on the problem set. We saw one with preventative war on a problem set, and now we'll be talking about the incomplete information cause of war in today's lecture. In the B block, I want to introduce a straightforward deterrence model with incomplete information that is essentially a signaling model. It'll be your first signaling model, and you'll see exactly why we call it a signaling model once I've got it drawn up on the screen. I'll introduce the key ideas. It's not a super difficult model. It'll essentially be two separate deterrence models where one player knows which deterrence game they're playing and one doesn't. It'll be relatively straightforward in that sense, but I will have to show you an additional trick in terms of how we interpret strategies and what that role that has in the beliefs that the uninformed player winds up having. Here, the uninformed player won't just have a prior belief, they will have a new data point in seeing whether or not their opponent issued a challenge. That challenge that an opponent might issue in a deterrence game is itself an opportunity to send a signal about how strong you are. In the C block, we'll do some equilibrium analysis for pure strategies in that signaling model that we just introduced. So we'll see that different kinds of strategies, pooling strategies, separating strategies, yield different kinds of beliefs, different kinds of inferences drawn by the uninformed player, and we'll see that those differences in the inferences drawn will have big ramifications in terms of what the equilibrium outcomes will be. So whether the informed player moves first or second, that'll be A block versus B and C blocks. And then in the C block, we'll see there's all sorts of different substantive stories that one can tell using a straightforward signaling model. So I hope that this is something that's pretty fun. There's going to be some parts where you might furrow your brow just because this is new. This is going to be a slightly different style of analysis, but it's nothing too tough. I know about your skills enough by now. I know that you can learn things pretty quickly. And so if you're just patient, if you give yourself some time, if you allow the osmosis to happen, I think you might have a good chance of learning some really cool lessons today. Let's get started. All right, so here in the A block, I want to revisit the standard model that we discussed at the end of last week's lecture. So let me just cue up some more blue around me. The less of this face that you see directly, the better, right? That blue really helps. And look how cool this looks. That looks pretty cool. And let's get into it. So remember, at the beginning of time, nature makes a move. Nature decides what state of the world we're going to find ourselves in. And in particular, nature is going to tell us whether or not state B has low war costs or high war costs. In other words, are they very resolved or are they not so resolved? Are they strong? Are they weak? Are they tough? Are they not so tough? And we'll say, I think in the last week's lecture I had it 50-50, I really want to show you the importance of this probability. Let's say that nature chooses low costs alpha percent of the time, with probability alpha, where that's somewhere between 0 and 1, strictly so, otherwise there wouldn't be any private information. Right? So with probability alpha, state B has lower war costs. So alpha percent of the time we have low war costs, and therefore 1 minus alpha percent of the time. With probability 1 minus alpha, we have high war costs. Where does this alpha come from? Well, it could be purely subjective, right? It could be that is just the probability that state B is going to know what state of the world we're in, so they don't need an alpha. They're not going to have probabilistic expectations over that. So it could just be some subjective belief that state A assigns to low war costs versus high war costs. It could be something based on some predictions that they have. Maybe they've got some statisticians somewhere at the State Department just crunching numbers. And even though they can't come up with pure predictions about how strong they think or how high or low the costs for state B are, even if they don't know that, they can still use some model to try to come up with the best prediction that they can. Or it might be somewhere in between where it's like, oh, well, I know that countries a lot like country B in years a lot like this one all have low war costs, or 60% of the time they have low war costs, or something like that. So that's the idea, is that state A is just assigning some correct probability to the likelihood of seeing low war costs or high war costs. Regardless, state A then has to make some decisions. So state A is the next player to move. And remember, state A is linked via an information set. So they don't know the state of the world. They don't know which of these two decision nodes they're at. Okay? So state A doesn't know if we have low war costs or high war costs. That's something that's private to state B. State B knows their costs and state A doesn't. All the same, state A has to make an ultimatum offer. So state A doesn't observe the state of the world. However, they have to choose some X between 0 and 1. Now remember, because this is an information set, state A makes one and only one choice. They don't get to condition their choices on the state of the world because they don't know the state of the world. They don't know which game we're playing. Just for completeness sake, because there's nothing to update on, I just want to show you this is going to be useful in the B and C block. But just for now, I'm going to say state A thinks that they're this decision node with probability alpha. They use the correct probability. They think they're here alpha percent of the time, which is true. And they think that we're in the high cost world. They think they're at this decision node with probability 1 minus alpha. That's going to be an important component for an expected utility calculation for them moving on later on. So they choose one X out of this Assassin's Creed hoodie. They choose some between 0 and 1. Here comes the coolest trick. This is when I knew that I had gone way too far, right? So they could choose X equals 0, X equals 1, X equals 1/2. This is when you know I've got way too much time on my hands. Once I start doing this, so they choose one of these. No matter the state of the world, after state A chooses their X, state B gets to make a choice. And state B knows the state of the world. State B knows their own war costs. And per usual, state B can either accept the offer or reject the offer. Okay? If they accept the offer, then state A gets X and state B gets 1 minus X. This is just as efficient and ultimatum-y looking as ever. In the world with low costs, state A, if there's a war, if state B rejects, then state A gets P minus CA, just like always. And state B gets 1 minus P minus CB superscript L, the lower of the two war costs. So here in low cost world, they pay the low war costs. That's just some number. We've been using CB as a variable all the time. Right? Now now there's going to be two of them, and state B knows which of them it is, and state A doesn't. And you're like, boy, I feel like I have a lot in common with state A. No, you have more in common with state B. You're the analyst. Similarly, over in the high cost world, if there's a war, if state B rejects, then state A gets P minus CA, just like always. And state B gets 1 minus P minus CBH, the higher of the two war costs. So throughout, we're going to say that CBH is strictly greater than CBL is strictly greater than 0. So the high war costs are higher than the low war costs, and they're both war costs, so they're positive. We could do this whole same analysis with the uncertainty on P instead of the C's. Now, that just makes it a little bit harder because it can't just be that state B knows something about P that state A doesn't, right? Then they'd have to agree to disagree, which is generally frowned upon. So instead, you'd have to say like, oh, well, maybe P depends on A's army and B's army, and there's something about the size of B's army that A doesn't know. And next thing you know, we have fractions, and we've learned the hard way that fractions just aren't a strong suit for any of us. It's just easier to talk about CB. However, you can imagine doing the same model with the private information about something about military capacity so that you are influencing the probability of victory rather than the costs. This is more like, how prepared are you? How much of an army have you built up so that you don't have to arm as much now? Or what's your industrial capacity now? Could you easily produce enough for the wartime effort? There's a lot of ways to reduce costs in terms of fighting fights. This is something that isn't studied enough, if you ask me. We need to know more about cost-cutting mechanisms, both in terms of preparation for the day-to-day peacetime economy and also during mobilized economies. Okay, so here's our model. This is our model. And look, it's just two ultimatum games, but where state A doesn't know which ultimatum offer they're making. State B, they get to accept or reject. They're going to make two separate decisions. They could accept or reject in the low-cost world. They can accept or reject in the high-cost world. And they'll be able to set two different criteria because they know their type. That's the whole point. So let's just zoom in on the low-cost world. Let's figure out when state B is going to accept the offer versus when they're going to reject the offer. If you need to go back to Ultimatum Week video, it's right there. Right? We can talk about the hoodie and Chancellor Jones and all the different things. Well, at this point in time, state B, the low-cost type of state B, has observed some offer X, and they can either accept it and get 1 minus X happiness points, or they can reject it and get 1 minus P minus CBL happiness points. I'm going to proceed throughout today's lecture saying that the state B accepts when indifferent. That's a result. That's not an assumption. That's a result. Go back to the video. Go back to the ultimatum game video. So we'll say that the low-cost version of state B accepts the offer when X is less than or equal to P plus CBL. This is the same as it's been before. In other words, there's going to be two different criteria for accepting offers for the low-cost type and the high-cost type. So here the threshold is P plus CBL. So they need X to be less than or equal to P plus CBL, otherwise they'll want to fight. Let's go over to the high-cost type. Well, the high-cost type is thinking to themselves, I can either accept this offer and get 1 minus X, or I can reject this offer and fight a war, and in expectation, I'll get 1 minus P minus CBH, the high costs. I pay higher costs. The high cost type pays higher costs. Otherwise, why did they name themselves that? Same logic as before. We'll see that the high cost type accepts so long as X is less than or equal to P plus CBH. Now look, let me call your attention to one thing. So the low cost type accepts if X is less than or equal to X plus CBL, and the high cost type accepts if X is less than or equal to X plus CBH, right? So the high cost type, there's more offers that they'll accept, right? There are offers, so every time that the low cost type would accept an offer, so too would the high cost type. So for example, if X was equal to 0, right? If state A was like, you know what, I'm going to be super cautious, I don't want any of the dollar, you take the dollar. This dollar is poisonous, apparently. Okay, so if state A said that, then state B, both the low-cost type and the high-cost type would accept that. And that will be true for every X up to P plus CBL, the lower of the two thresholds. Right, CBL is less than CBH, and so P plus CBL is the lower of the two thresholds. So for every x short of that, both types would accept. Now, if x is strictly greater than p plus cbl, but less than or equal to p plus cbh, which is a range, we know that's a range. So if x lives in that region, then the low-cost type attacks, they reject the offer, and the high-cost type accepts. Finally, if x is strictly greater than p plus cbh, then both types of state B would prefer to reject the offer. So in other words, if we take x on the horizontal axis, we can partition 0, 1. We can partition all the possible offers. We can partition the set of all possible offers. We can partition it into 3 zones. There's the zone where both types would accept. There's the zone where the low-cost type would reject and the high-cost type would accept. And there's the zone where they both reject. This is a little bit more nuanced than it was before. Now there's this middle zone. Right before, again, if you went back to ultimatum week, which is an if, but if you went back, you'd remember that it was like, there's one zone where things get better, and then there's another zone where offers get rejected, and there's just the war discontinuity, right? Here, there's 3 zones. We're going to have to think those through in terms of how the offer X, what does that wind up with? What does that generate for state A? We need to think about the optimal offer that state A could make, right? We've handled both types of state B. Now, the next thing in backward induction is go up to the information set that state A controls. They don't know which node they're at, and we need to think through what's their utility going to be at each of these. That's something, right? This is getting nuanced. So let's think through these 3 zones. 3 zones. This is just like my lighting setup in here. 3 zone lighting. Splashed my water way too aggressively and now it's on my glasses. I'll make the director's cut. So let's think about this. If I offered x equals 0, I'm state A now. I'm the very confused state A. I'm incredibly confused and you're like, that isn't very hard for me to believe. So if I'm state A, so if I offer x equals 0, with probability alpha, I'm up against the low-cost type who accepts x equals 0, and I get 0. And with probability 1 minus alpha, I'm up against the high-cost type who accepts, and I get 0. So if I offer 0, the low-cost type accepts, the high-cost type accepts, I get 0. If I offer some number that is strictly positive but less than p plus cbl, right, let's say it's halfway in between, then with probability alpha, I'm up against the low-cost type, and they accept it, and I get that offer. And with probability 1 minus alpha, I'm up against the low-cost type, and they accept it, and I get that offer, right? So in other words, up through P plus CBL, I'm still on the 45-degree line, just like I was before, right? So I start at 0, and I ride the 45-degree line up to P plus CBL, the first threshold. The first threshold. This is starting to sound like a video game or something. You're like, yeah, that's what I thought game theory was. So I'm up through that. Remember, we are acting on the principle that state B, both types of state B accept when indifferent, and so this goes all the way up to that point. So I also have a top of the mountain. It might not be the top of the mountain, but I have got a top of a mountain at P plus CB. Okay? So for everything in this zone, that's how it plays out. So I now have a best candidate in this zone, right? Of all of the offers, from state A's perspective, the best offer that lives in this zone is P plus CBL. I'm not going to offer 0. I'm not going to offer P plus CBL over 2. I'm not going to offer P plus CBL over 3 or 4. I'm not going to offer anything in between. I'm going to offer the best of all of the things in zone 1 is P plus CBL. The low cost type accepts that. The high cost types accept that. In other words, this is my best certifiably peaceable offer. This is the best offer I can make that guarantees peace against both types. You're like, oh, that sounds foreboding. Oh, it's foreboding. You should feel very foreboded right now. That's not a word. Okay? So this offer, P plus CBL, that you can lock peace in. You could lock peace in right now. You could lock peace in. You could lock peace in. Now, just in the name of keeping the drama high, let me switch over to zone 3. And you're like, oh, you're killing me with all of this drama. These cliffhanger endings. And is there going to be a commercial break sometime soon or something? Hello. So here we are in zone 3. So suppose that I make an offer strictly greater than P plus CBH. I choose some X greater than that. I'm going to be pretty greedy. I'm going to choose this big ol' X. I'm going to choose some X strictly greater than P plus CBH. That's going to be such a bad offer that it pisses off not just the low-cost type of state B, but also the high-cost type. Both types are rejecting in zone 3. So here in zone 3, both types reject. So with probability alpha, I'm up against the low-cost type of state B, who rejects offers in this zone. And I get utility P minus CA. That's my expected utility of OR. And with probability 1 minus alpha, I'm up against the high-cost type of state B, whom I've managed to piss off too. And they reject the offer, and we go to war, and I get P minus CA. So alpha times P minus CA, plus 1 minus alpha times P minus CA, is just P minus CA. I get my war payoff over here. I just get my war payoff for sure. It doesn't depend on X. We go to war either way. And we know that P minus CA is less than P plus CBL, which is what I get for my lock-in peace offer. So in other words, there will not be any offers, there will not be an equilibrium where state A makes some offer that irritates both states, both types of state B. There will not be an offer where state A makes an offer so high that the high type of state B rejects, and therefore so too does the low-cost type of state B. They're not going to do that, right? That's just too costly. They could lock in peace. And now here we are in zone, I forget if it was B or 2. I've already lost track. I really got to start scripting these things. I feel like Buzz in Home Alone, A, 2, and D. So here we are in this region, let's say zone 2. Now I can sleep at night. Now what happens in this zone? So this zone, this is strictly greater than P plus CBL, and therefore the low type rejects offers here. And it's less than or equal to P plus CBH, so that the high cost type accepts offers here. So with probability alpha, you get rejected. And with probability 1 minus alpha, you get accepted. So because of that, then there's a little drop down, right? Unless alpha was exactly equal to 1, there's going to be a little bit of a hit, right? So because we're rejecting, this is still just a hypothetical, but sort of the end point of what's going to happen in this region, the end point, what this drops down to is P minus alpha CA plus 1 minus alpha CB, right? So there's a little drop down depending on alpha and CA versus CBL. So there's a little drop down. So what's going on in the region is with probability alpha, you're up against the low cost type who is rejecting offers in zone 2. And so it's alpha times P minus CA, which a lot like over here doesn't depend on X, right? So some component is just the intercept, right? That tells you the intercept of the line I'm about to draw. And with probability 1 minus alpha, for every X that you could choose in here, you're up against the high cost type who accepts offers in this region, right? And so we wind up with 1 minus alpha times X. So we take a little drop down, right? You'll notice we have a little drop down. And then after that, we go up as X goes up again. However, we don't go up at the same rate. So over here in zone 1, we were going up with a slope of 1, right? So the equilibrium payoff, the change in the equilibrium payoff for state A, as X was getting bigger and bigger, so too was their payoff. However, here it's flatter because now the slope of the line is 1 minus alpha, right? But it's still positive, right? So alpha is somewhere strictly between 0 and 1, and so Consequently, we have a positive line. It might be really flat if alpha is really close to 1, and therefore we think it's the low cost, and therefore it's the low cost type more often than not. Or it might be really close to 1 if alpha is really close to 0, and so we have the high cost type more often than not. And so we wind up going back up. And then we reach that magical point, P plus CBH. P plus CBH, that's the upper bound of zone 2. The high cost type we assume accepts when indifferent. And so we've got a top of this mountain. What's the associated utility? So here you have made the offer P plus CBH. So with probability alpha, you're up against the low cost type who rejects that offer. You tried to keep too much. The low cost type says, no, I'd rather reject that offer. I'd rather fight a war. So they reject that. So with probability alpha, you get P minus CA. And with probability 1 minus alpha, you're up against the high cost type who accepts this offer. They're exactly indifferent at this offer, right? And you get P plus CBH. So that's your expected utility of your state A for making this offer, the semi-greedy offer. The offer that you know induces war with the low-cost type and renders the high-cost type exactly indifferent. So you've got the lock-in peace offer and you've got the semi-greedy offer. And these are the two respective tops of the mountains. We have two mountaintops, right? We know it's not going to be any of the P minus CAs. We know it's not going to be anything between 0 and P plus CBL. We know you can rule all these out. This line and this flat line, you can just rule them out. You can rule off everything in the interior here because there's always something better. We have two mountaintops and we don't know which one is higher. We have two mountaintops and we don't know which one is higher. The answer about which mountaintop is higher, it depends. Notice, however, before we get too deep into it, this mountain is a peaceful mountain. And this mountain has war in it alpha percent of the time. Getting pretty cool. Well, okay, so this mountain, the altitude of this mountain, the altitude of the lock-in, peaceful, surefire, peaceful offer, at this offer, state A offers P plus CBL, which the low-cost type accepts and the high-cost type accepts, and therefore state A gets to keep P plus CBL. They have P plus CBL. That's their utility here. That's not an expected utility. They get that for sure. Over here, however, it's alpha times P minus CA plus 1 minus alpha times P plus CBH, semi-greedy offer. That's an expected utility because you don't know what type you're up against. Sometimes you go to war, and sometimes you don't. Well, you'll make the safe offer, you'll make the peaceful offer if P plus CBL is greater than or equal to alpha times P minus CA plus 1 minus alpha times P plus CBH. You work it all out. I'm going to put this in terms of alpha. So you work this all out, ka-chunka, chunka, chunka, and you will choose the peaceful offer. You will choose the safe, all the way peaceful offer if alpha is sufficiently high. If you think you're up against the low cost type sufficiently often. In particular, alpha needs to be greater than or equal to CBH minus CBL over CA plus CBH. So that tells us how high alpha needs to be. How likely does the low cost type have to be to want to make peace with the peace offer? And how unlikely does the low cost type have to be to make state A want to make war sometimes with the semi-greedy offer? So let's just put this in terms of alpha. I just want to make a 0, 1. So here's 0, 1. Everything to the left of this alpha star leads to war. It means alpha wasn't high enough. And everything to the right means we have peace. That means alpha was high enough. This is alpha star. That's the threshold that we just computed. And so we wind up with 3 comparative statics about how often war happens in this model. As CBH gets bigger, which is to say, as the high type's costs get even higher, this threshold increases and war becomes more likely. You increase somebody's war costs and war becomes more likely. That's a little bit weird when you think about it. We take the weaker version of state B, we make them even weaker, and there's more war. Even though we never go to war with the high-cost type of state B. The high-cost type of state B never goes to war. They either accept the safe offer or they accept the semi-greedy. However, as CBL, as the low type of state B's costs increase, as we make the low-cost type have to pay higher costs when they fight, as we make them less low cost, war becomes less likely. They accept more offers. They're more pliant. And of course, if you increase CA, if you increase state A's war costs, war happens less frequently as well. All of those things move this threshold, which tells you how likely war is and how likely peace is. So in other words, the prior belief, how likely you think it is that we have a low-cost type versus a high-cost type. Let's say that you're correct. In this case, we're assuming that you're even correct. You're using the objective and correct probability. If you do that, you can still have war happen. Nobody did anything wrong here. All that happened was State A could either take peace for sure, except it was pretty expensive. They could either buy off the low-cost type, or they could buy off the high-cost type on the understanding that the low-cost type was going to attack them. Now, if alpha is low, so they don't think they're up against the low-cost type all that often, then they don't care. So part of the argument for mutual optimism is that how war happens here is State B knows that they're the low-cost type, so they're optimistic for good reason. And alpha is low. So State A thinks it's unlikely that they're up against the low-cost type. So there's a mismatch. War happens in this model if State A thinks that it's unlikely they're up against the low-cost type, and they're wrong. They're up against the low-cost type. There's no war with the high-cost type. You only fight wars against the low-cost type. And the reason that happens is if you think alpha is low, where we have a precise sense about how low it needs to be, depending on the costs of the three players, the two types of State B and State A, notice that that's what's determining the threshold of the costs. These costs are combining in a way to tell you how likely you have to think it is that you're up against a strong opponent for you to act like a jerk. And then if you act like a jerk against an opponent that actually turns out to be strong, therefore surprising you with respect to your alpha, then you get hit. So if the uninformed player moves first, this gives them an incentive to engage in thinking that you might call a risk-reward trade-off. They could buy peace for sure by buying off the low-cost version of State B, and therefore also buying off the high-cost version. But 1 minus alpha percent of the time, they're like, man, I overspent for this piece. 1 minus alpha percent of the time, they're up against the high-cost type, and they're like, man, why did I act as if I was up against the low-cost type? Now I've got buyer's remorse. You could buy peace, but it's expensive. Or you could introduce a little risk. For a little bit less, if you want to keep that X, okay, well, if you're up against the high-cost type, then you get to enjoy all of that X. And if you're up against the low-cost type, you're That's something. So that's a pretty cool model. I think that's a pretty cool model. This is, so this was first introduced when the bargaining model of war was really in its infancy. This is sort of Baby's first incomplete information cause of war sort of model. Here, war happens some of the time. It doesn't happen all the time. It happens some of the time. It depends on whether or not we actually get the low type, and it depends on whether or not that's a surprise with respect to the costs. But you could simulate this. So you could write a computer program, and all it has to do is read in alpha, CA. Notice that the P doesn't matter. All the P does is sort of, you could take the zones, and all P does is move them like this, but the bands don't change, right? The zones are the same. We just move where the zones are. But if we actually change the C's, then we get different zones, and we get different heights of the mountains and all that sort of stuff. What is this all about? But anyway, you could write down the three costs, alpha and P, and be able to figure out how often, what percent of the time, depending on how you think these things are distributed, what percent of the time war happens. But it's not zero, right? Regular ultimatum game, war happens 0% of the time. This ultimatum game, war happens some percent of the time strictly greater than 0. We just made war happen. Incomplete information is a cause of war. Not knowing your enemy's war costs is a cause of war. Not knowing how strong they are. Again, I could do this on the P's instead of the C's. Not knowing about weapons that they have is a cause of war. There's a lot of wars that are well explained on the informational side. Well, now that we've seen how tricky it is for the uninformed player to move first, let's see if it's any easier on them if they move second. See you over in the B block. Alright, so here in the B block, we shouldn't be here too long. I just want to show you a model where the uninformed player moves second, and then we can discuss the wrinkles that causes in terms of how one might analyze it. So this will be your first example of what's called a signaling model. A signaling model has a couple of different things in common. First of all, there's two players. Second of all, there's one-sided incomplete information, so one player knows the state of the world and one player doesn't. And finally, the informed player moves first, so that the uninformed player has a chance to update their beliefs. They're going to go from alpha maybe to something else. They're going to go from their prior belief of being up against one type of the informed player or the other. They're going to have a chance to update their beliefs potentially, to think about what they believe conditional on what they saw. We're going to have to do some conditional probability. I will always provide the formula that you need to do the conditional probability. It's called Bayes' rule. I'll always provide that for you, and it'll just be a matter about using that machine effectively. So let me just show you a simple, straightforward model of signaling. So at the beginning of time, nature makes a move. Nature chooses the state of the world. In broad brushstrokes, just to keep I'm so tired of saying high cost type and low cost type. I already am tired of myself, and I haven't even edited the movie yet. So we'll just say that with probability alpha, state A is strong. So here state A is going to have the private information and state B isn't. State A is the informed player this time. So with probability alpha, state A is strong. And with probability 1 minus alpha, state B is weak. Where again, alpha is somewhere strictly between 0 and 1. Otherwise, there wouldn't be any private information. State B would know just as much as state A does. So state A observes their type. They get to see this, and then essentially they're going to be player 1 in a deterrence model. If you need to go back to extensive form games week, that doesn't mean you're going to, but it's there. So the idea here is that just with a lot of these finger games, state A is either going to be able to opt out or opt in. So we'll say that no matter what state of the world we find ourselves in, state A cannot issue any challenges. They cannot issue a challenge, which is going to take us to a terminal node. That'll be a status quo. And to keep things spicy, I'm going to have the status quo be different across the two states of the world. And you're like, oh, spicy is a strong word, isn't it? Or they can issue a challenge, just like in any deterrence model. So state A can issue a challenge. And if state A issues a challenge, then state B will get a chance to make a move. Here's the thing. They don't know which world we're in. But now they only get here. State B only has a choice to make. State B only has a choice to make if state A challenged. They just don't know which version of they show up to work one day. Apparently state B now is a worker. So they show up to work one day and they have a challenge on their desk. And it says, I challenge you, signed state A. The thing is, state A wasn't nice enough to say how strong they were. It just says signed state. So now state B has to make a decision, but they don't know what kind of state A they're up against. But now they know that a challenge was made. What if they were living in a world where only strong state A's challenged and weak state A's didn't challenge? Well, if that was the case, then this would be easy, right? But what if both types were challenging? What if neither type was challenging? In which case, I don't know why they're at their work desk with a challenge in their hand. But we're going to have a lot to think through here. So it isn't going to be the case, necessarily, that state B thinks that they're up against a strong version of state A with probability alpha. They might have a chance to update their beliefs. I'm going to call the probability that state B thinks that they're at this decision node, which is to say, the probability that they think they're up against the strong type of state A, conditional on observing a challenge. I'm going to call this probability mu. And therefore, they think that they're at this node with probability 1 minus mu. This is going to be endogenous. Mu is going to be endogenous. Alpha gets handed to you. I give you alpha at the beginning of time. Okay? I give you alpha. Alpha is outside of the model. Alpha is one of the things that you're given. But mu is going to depend on some things inside the model, and I'll show you this momentarily. Okay? So with probability mu, we're at this decision node, and with probability 1 minus mu, we're at this decision node, according to state B. Regardless, state B has the choice to make. They can either acquiesce to the challenge, or they can fight. So it really is two deterrence models. It's two deterrence models. It's just that, first of all, I've, sort of done this to them. And second of all, state B doesn't know which deterrence game we're playing. That sounds that sounds pretty realistic, right? Somebody comes up to you and they're like, "What's up? You want to fight?" And then you got to think to yourself, I don't know how strong this person is. I was just sitting here at the Potbelly trying to get myself a sandwich. And somebody just rocked up and tried to fight me. And I don't know the first thing about them, except for the fact that they challenged me. I now have a data point about them. Now let me fill in some preferences. I taught this model to my other class 2 weeks ago. And so this is a model of poker that I'm amending by making this a little bit more straightforward in terms of I'm trying to make it more substantive with the labels, but I'm trying to keep it super simple just by using numbers here instead of variables and P's and C's. We'll put P's and C's on a model like this next week. I just want this to, there's enough new stuff that I want this to be easy. So this will be just like poker, right? So you can imagine the strong type of state A being somebody with a high card or a good hand. And you can imagine the low type as somebody with a bad hand. Okay. The question is, do they want to bluff? So we'll say that if the strong type doesn't challenge, right, then at the status quo there, they get 1 happiness point and state B gets -1 happiness points. And in the world where the weak, and what happens if the weak version of state A doesn't issue a challenge, then they get -1 happiness points and state B gets 1 happiness point. So the idea here is the strong version of state A, not only are they strong, but they also like the status quo. Whereas the weak version of state A doesn't like the status quo. That's a -1 for them. Now, let's go down to the worlds where state B has had a chance to make a choice. In either situation, if state B acquiesces, that's the equivalent of folding in poker, and we wind up with 1 happiness point for state A and -1 happiness points for state B. Now, if state B tries to fight the strong version of state A, that's real bad. So then the strong version of state A gets 2 happiness points, and state B gets -2 happiness points. However, if state B fights the weak version of state A, then the weak type gets -2 happiness points, and state B gets 2 happiness points. It really is, you'll see, this is a zero-sum game, and the story aligns perfectly with poker, and Clausewitz compared all the war to poker, so I feel very comfortable teaching you this model of poker. So the main idea of an analysis in a model like this is that we need to think about what state B is going to do as a function of their beliefs, mu, and then we'll think about what that means the state A is, the two types of state A are going to want to do. The main tool that we use to compute mu, whenever we have a chance to, okay, so the rules of Bayesian analysis are that you have to use Bayes' rule, which I'm about to show you, whenever you have a chance to, which is to say, if state B ever gets hit on the path of play, if this information set ever gets hit along the path of play, then state B has to update their beliefs according to Bayes' rule, which is a formula for how to get that conditional probability we were just talking about. So mu is just the probability of seeing the strong type of state A conditional on seeing them issue a challenge. So you see them issue a challenge, you get a new piece of data. How do you update your beliefs in a principled way? Here's the principled way. And it's going to be just a pretty simple fraction. It's going to have 6 total components. Be cool, it's okay. So the probability of it being the strong type conditional on seeing a challenge is, in the numerator, it's just the probability of seeing the strong type at all times the probability of seeing a challenge conditional on it being the strong type, which is to say, what strategy is the strong type playing? So the probability of seeing the strong type, that's alpha. That was your prior belief. That was given to you. So you start off with an alpha belief about seeing the strong type. Now you've got new data in the form of this challenge. Are you going to update to something bigger than alpha, smaller than alpha, exactly equal to alpha? We're going to see. So the numerator is just the probability of being the strong type, which is alpha, times the probability of challenging conditional on being the strong type, which is going to depend on the strategy played, over that same thing, probability of seeing the strong type, which is its alpha, times the probability of challenging conditional on being the strong type, which is going to depend on the strategy that we're studying, plus the probability of seeing the weak type, which is 1 minus alpha, times the probability of observing a challenge conditional on being the weak type, which, again, is going to depend on the strategies played. We're going to have a couple of opportunities to use this formula today. By the end of the next 3 weeks, you're going to be tired. This is going to be boring for you. I know that it looks a little bit scary on the page. I know that some of this notation is new for some of you. Don't worry about it. It's not that complicated, and I will always provide the formula. And remember, half of the things in here are given to you. The probabilities of seeing strong or weak, that's alpha and 1 minus alpha every time. Don't worry about that. The question is, how do differences in the strategies change what state B thinks is coming in terms of who they're up against? Now, whether we compute mu via Bayes' rule or otherwise, we can still pin down what state B wants to do as a function of mu. Remember, mu is just a probability. It's the probability of seeing the strong type conditional on arrays. Okay? So let's just figure out while we're here, does state B want to acquiesce to the challenge or do they want to fight? Well, let's get some expected utilities. So the expected utility of acquiescing. With probability mu, you're up against the strong type, and if you acquiesce, you get minus 1 happiness points. And with probability 1 minus mu, you're up against the weak type, and you get minus 1 for acquiescing. So if you acquiesce, you get minus 1 for sure. Minus 1 for sure. Minus 1 here, minus 1 here. It's minus 1 no matter what you do. Minus 1 if you acquiesce. That's the surefire thing. Nobody ever says, oh boy, I really hope I'm up against the right person as I acquiesce to them. No, you say that as you start to fight them. Or maybe just before you start to fight them. I don't know. I haven't been in a fight in a while. Chewy is the weak type. So the expected utility of fighting. Well, with probability mu, you're up against the strong type. And if you fight them, you get minus 2 happiness points. So minus 2 times mu. That's not a good start. Plus 1 minus mu percent of the time, you're up against the weak type, and if you fight them, you get 2 happiness points. So 2 times 1 minus mu. That works out to 2 minus 4 mu. Notice that if mu is equal to 0, that will be 2, which is what you get for fighting the weak type. And if mu is equal to 1, that will be minus 2, which is what you get for fighting the strong type. Intermediate mu, intermediate happiness. It's a well-known maxim. So that works out to you would rather fight if mu was less than or equal to 3/4, and you'd rather acquiesce if mu was greater than or equal to 3/4. So if you think mu is high, if you think it's very likely that you're up against the strong type, you don't fight. Otherwise, you fight. That's going to be the same throughout. So we can just pin that down. That's not going to change. That's just how it is. Now, one final thing before we start analyzing, I just want to talk about 2 classes of pure strategies for state A. Notice that state A, because they know their type, they can condition their choices on the type, which is to say, the strong type makes one choice, and the weak type makes one choice. They can make the same choice, they can make different choices, but the whole thing is you're allowed to condition on what you know. Think about different columns in the trade war game. So there are 4 possible combinations of pure strategies. Right? It could be that both types challenge. It could be that both types stay out. Those are referred to as pooling strategies. We could say that the 2 types pool on challenging, or that the 2 types pool on not challenging. Pooling strategies are strategies where all types do the same thing. Two types pool on challenging or pool on not challenging. In contrast, the other two make for different choices by different types. It could be that the strong type challenges and the weak type doesn't challenge, probably what you might have expected. Or vice versa. It could be the counterintuitive world where the strong type doesn't challenge and the weak type challenges. These are referred to as separating strategies. Separating strategies. The two types separate themselves. They do different things. They do different things. They separate. We're going to see that pooling and separating strategies have immense ramifications on the beliefs that state B has, and therefore on the choices that state B has, and therefore on the choices that state A must make. So let's work our way through that over in the C block. Okay, so the way that we do this is it's sort of like forward and then backward and then forward induction. We're much more active analysts in a signaling model. So here's how it's going to go. We're going to posit a strategy for state A. We're going to say, okay, first things first, let's check to see if a given strategy by state A is supportable in equilibrium. Right? So now, instead of saying, I'm going to find all the equilibria, now it's like, do there exist equilibria that satisfy certain properties? So our enterprise shifts somewhat. Instead of like, here's a game and you solve it, to here's a game and you poke at it. And along the way, you're solving it and you're learning from it, but it's a different style of analysis. You'll see what I mean here in a second. It's pretty cool, I think. So just as an example, let's check to see if there exist any perfect Bayesian equilibria, that's what we call these, where both types challenge. The strong type challenges, the weak type challenges. So let's fix that. Let's lock that in. Let's check that first. Okay, so we're checking to see if there exists an equilibrium where both types challenge. We're going to try to construct one. So now it's like, have something in mind and then check to see if you can do a construction project. Okay, so that's step one, is posit some strategy by both types of state A. Now, what does that mean for the beliefs? What does that mean for state B's beliefs? Because now both types, the strong type is challenging, the weak type is challenging. What's the appropriate mu? What mu if they knew that everybody was challenging? If state B knew that everybody was challenging, and then they saw a challenge, what probability would they assign to the strong type? You can pause the video if you need to. You can go to Bayes' rule if you need to. That's what I'm going to be doing once you're back from pausing the video. Or you can just think about it for a second. If you knew that there was a 75% chance that you're up against the strong type and a 25% chance you're up against the weak type, let alpha be 0.75. If you knew that was true, and you also knew that every type of state A would challenge you, and then you saw a challenge on your desk, your state B at work again, and you see a challenge, what probability would you assign to it being a strong type? Welcome back. Well, you'd assume it would be alpha. Just alpha would go right through, right? So you wouldn't learn anything. It would be an uninformative signal. If everybody was doing the same thing, then that thing doesn't teach you anything. Pooling strategies, this is pooling on challenge. Pooling strategies, you don't learn anything from the signal. Pooling, if a signal involves pooling, if everybody is doing the same thing, then you don't learn anything. If everybody on the road had on their left turn signal, which it seems like is happening a lot. If everybody on the road had on their left turn signal, now you know they're not all going to turn left right now. Now you just ignore that. Eventually you would just go a little bit crazy from looking at the flashing light that doesn't have any meaning. That light would have no meaning, right? Let me show you how that works out in Bayes' rule. So let's get mu. Let's get mu conditional on this strategy. Conditional on the strategy of pooling on challenge. Well, remember, here's our formula for, this is Bayes' rule. This gives us the mu. Every time that we hit this, it gives us the mu. So this probability is the probability of seeing the strong type, which is alpha. That was given to us. That's exogenous. That never changes. Times the probability of seeing a challenge from the strong type. Well, we just said the strategy tells us that the strong type is always challenging. So the probability of challenge conditional on the strong type is 1. So that's alpha times 1 over. Same thing over here. Right? So this is alpha, this is 1. Alpha times 1. Probability of seeing the strong type is alpha. The probability of challenging conditional on being the strong type is 1. Plus, well, the probability of seeing the weak type is 1 minus alpha. And the probability of challenging conditional on being the weak type in this strategy, we are studying pooling on challenge. Therefore, the weak type is challenging with probability 1. So we have alpha times 1 over alpha times 1 plus 1 minus alpha times 1. That's alpha over alpha plus 1 minus alpha, which is alpha over 1, which is alpha. We learned nothing. We have the exact same beliefs that we had going into the interaction. Observing a challenge taught us nothing. Pooling strategies mean that there is no signal in the noise. So, whether or not we see a fight or an acquiesce depends on alpha. Because mu equals alpha right now. If alpha is less than or equal to 3/4, and thus mu is less than or equal to 3/4, well, we've already decided that means that state B will fight. So if they think it's unlikely that they're up against a strong opponent, they fight. They make one and only one choice, right? So you can those get locked in. And so now the question is, does either type of state A want to deviate from this state of affairs? Do they wish that they could change their mind? Because right now they know what they're going to get. Well, right now the strong type, they're issuing a challenge. Because alpha is low, mu is low, which means fighting is happening, and the strong type is happy as a clam because they get 2 happiness points. They don't want to deviate. They're good. Nothing to worry about there. They're good. They're satisfied. So the strong type is good. State B is good. What about the low type? What about the weak type? Well, the weak type right now, they issued a challenge. Alpha was low, which meant mu was low, which meant a fight happened. And the weak type is getting -2 happiness points. If they had stayed out, they'd have gotten -1 happiness points. They never should have issued that challenge. This is not a perfect Bayesian equilibrium when alpha is low. Because the bluff gets called, the weak type is thinking to themselves, I'll just stay out. However, suppose instead that alpha was high. Suppose that alpha was greater than or equal to 3/4. Therefore, mu is also greater than or equal to 3/4. Therefore, state B acquiesces. They acquiesce because they're pretty sure they're up against the strong type. Let's see if either type wants to deviate now. Strong type, it's true that they don't like acquiescence as much as fighting, but they're getting 1 happiness point for the acquiescence. They'd get 1 happiness point if they hadn't issued any challenges. They don't have a profitable deviation. They're indifferent, but that's not profitable, so they don't want to deviate. They're good. Weak type. Well, the weak type, right now, acquiescence gets them 1 happiness point. If they had stayed out, they don't like the status quo. They'd get -1 happiness points. They don't want to deviate either. This is an equilibrium. This is a perfect Bayesian equilibrium. There are 4 components to the equilibrium. The 4 components go like this. We have a strategy for the strong type. The strong type challenges. We have a strategy for the weak type. The weak type challenges. We have a belief that comports with that strategy. Mu equals alpha. Right? So the strategies of the 2 types inform the appropriate belief for state B to have. State B's belief has to match with state A's choices. Okay, so state B's belief matches with this. We used Bayes' rule to turn the strategy of they pool on challenge. Then we said what mu comports with that. Mu equals alpha. Now we need a choice for state B that is sequentially rational, conditional on that correct belief. Acquiesce. Finally, we need to confirm that the original choices of state A, which informed the mu, which then informed the action taken by state B, neither of them wanted to deviate. Therefore, those 2 choices with that belief and that 1 choice by state B A perfect Bayesian equilibrium. The choices inform the beliefs inform the choices, information, time, together. It's all, you just see it all come together? Did you just see that? Signaling models are like one of those moments of like, so if alpha is sufficiently low, then we have a pooling equilibrium where both types challenge. Just for completeness sake, I want to check to see, I'm going to ask the following question rhetorically. Does there exist an equilibrium where the strong type challenges and the weak type doesn't? So we're going to check for a separating equilibrium. I'm wondering if there's a separating equilibrium in this model. So erase all the scratch paper. It's way easier to do on a screen. It's way easier to do. It's a lot of time, but at least I don't have to throw anything away. Well, what does that mean for the mu? Let's do the same thing. Let's say that you had a 75% chance of thinking. You go into this, you're thinking there's a 75% chance I'm up against a strong type in general. And then you learn that the strong types all challenge and the weak types all don't challenge. And then you show up and there's a challenge on your desk. What mu would you assign? How likely do you think you're up against the strong type if you know all strong types challenge and all weak types don't? Pause the video. You can use Bayes' rule if you need to. You can use just your brain if you need to. I'll be using Bayes' rule. I'm not very good with my brain, as you know by now. It's 1. It's 1. You know you're up against the high type for sure. You know you're up against the strong type for sure. You know you're up against the strong type for sure. Let's see that in Bayes' rule. So the numerator is the probability you're up against the strong type, that's just alpha, times the probability of seeing a challenge conditional on it being the strong type. In this separating strategy, that is 1. The strong types all challenge. So that's alpha times 1, just like before. Over that same thing, probability of the strong type, alpha. Probability of challenge conditional on strong type, 1. Plus probability of the weak type, that's 1 minus alpha, just like before. That doesn't change. Times the probability of seeing a challenge conditional on it being the weak type, which is 0. The weak types are not challenging in this separating strategy. Therefore, it's alpha over alpha plus 0, which is alpha over alpha, which is 1. So, pooling strategy, no use at all to the signal. Separating strategy, perfectly useful signal. We go from alpha, which is somewhere between 0 and 1. We have only probabilistic expectations about whether we're up against a strong type or a weak type, to perfectly 0 or 1. You get to draw a perfect inference. You know for sure who you're up against. So the only appropriate mu in this situation is 1. Well, what does that mean for what state B is going to do? Well, 1 is greater than 3/4. They're going to acquiesce for sure because they know for sure they're up against the strong type whom they don't want to fight. So they stay out. They acquiesce. State B acquiesces for sure. State B acquiesces. Now, when state B acquiesces, the strong type of state A, they're perfectly happy. It's not their best situation, but they're indifferent. They get 1 if they stayed out. They get 1 if they challenge. They don't care. But the weak type is thinking to themselves, well, I'm stuck up here with a -1. If I had issued a challenge, they would have acquiesced. State B would have acquiesced, and I'd get 1 happiness point. There does not exist an equilibrium where the strong type challenges and the weak type doesn't, because the weak type is going to observe the fact that they could have challenged and gotten an acquiescence. If we're playing poker and you have a bad card and you fold every time you have a bad card and you raise every time you have a good card. Every time you play poker, if you have a good hand, you raise, and if you have a bad hand, you fold. Well, then everybody is going to fold on you when you raise. They're going to know that you're strong for sure. They're not going to... But what that means is whenever you see that folding, then the version of you that had a bad hand is thinking to themselves, well, geez, I could have gotten them to fold. I could have gotten some money out of this. Same logic here. So there does not exist an equilibrium in this model where the weak type outs themselves as being weak. They're never going to say, oh yeah, no, I give up. Because that reveals too much. Moreover, that means that the strong type is getting revealed and being backed down to, and then the weak type is thinking, I could have faked it till I made it. That doesn't rhyme when you do it in past participle. I could have faked it till I made it, and that means something completely different. Yeah, I'm just screwed. No. I could have pretended. I could have mimicked. I could have acted like I was strong and enjoyed some of those benefits. I could have given myself a chance to get acquiescence. I could have given myself a chance for a 1. Now, if you're a weak country, you just walk around saying, oh, I fold, I fold, I fold. No challenges, no challenges. No, just tell us what to do. Please, no. No, you don't do that. You don't send signals perfectly. Nobody sends perfect signals. You don't see a whole lot of straight up separating equilibria in international relations. You don't see separating equilibria where strong countries act strong and weak countries are like, oh yeah, no, that's fine. But you wouldn't know that was absurd until you looked at it like this for a second or two, right? Now it's like straight up absurd to think, oh boy, I'm the strong type. I'm going to issue challenges. I'm the weak type. I'm not. I'm just going to sit here and twiddle my thumbs. Of course you don't do that. It's absurd. But it's only absurd when you looked at it like this. So we'll be talking about costly signaling on the problem set, and I hope that you enjoy seeing how costs help to make signaling mechanisms useful. It's a pretty fun idea. But this basic signaling model, this is the ultimate Mr. Potato Head doll. I mean, this gets twisted in all sorts of different ways. Signaling is one of the primary mechanisms that we study in all of political science, and especially in international relations, where I know something about myself and you don't, and the things that I do inform your inferences about me. That's signals, right? It's a huge deal. Well, now you know how to encode it. So what do we talk about today? Well, I think it was an interesting opportunity for us to juxtapose what happens if you're flying blind, like in the standard model that we talked about, versus what happens if you have an opportunity to send a signal, like in the B and C block. It isn't just a matter about who has information. It's about who has information and when do they get a chance to make a move. One thing that's interesting to think about isn't just about, state A versus state B and which one is informed and which one isn't, but also within the two types of whoever's the informed player. So let's think about the standard model for a second. So in the standard model, the informed player moved second. Now, if you were the low cost type, then you wish that you could tell. You wish that you could tell state A, hey, I'm the strong one. You should make me a good offer because I'm the strong one. I don't want to fight you. I literally don't want to fight you. The low cost type of state A does better if there's peace than if there's war. It's still a bargaining model of war. So the low cost version of state B wishes that there was some credible way for them to send information to state A that says, hey, make sure that you offer me P plus CBL. Make sure that you choose X equals P plus CBL, because if you choose anything higher, I'm going to reject and we're going to fight a war that I don't feel like fighting, but it's still in my own best interests. So in other words, if the informed player, if the low-cost version of state B in the standard model could, they would send a message, they would send a signal to state A that says, hey, I'm the low-cost type. You better be careful. Now, why wouldn't that work then? Right, because if that were the case, then the high-cost version would say, oh, I'm the low-cost version, you should make me a good offer too. There'd be mimicry, just like there was in the pooling equilibrium over in the C block. So there's an incentive to misrepresent. It isn't just private information. It's the fact that there's no reason to listen when somebody says, oh, and this is who I am. Just to repeat, in the standard model, the low-cost type would like to convey information to state A. But the high-cost type would like to lie. Because if they knew that the low-cost type was doing that, they would pretend to be the low-cost type as well. They would mimic. They would engage in cheap talk. And of course, we see that there's incentive to misrepresent in signaling models. We identified a pooling equilibrium where the weak version of state A behaved as if they were strong. They issued a challenge, not because they were interested in actually fighting the fight, but rather because they knew that it was unlikely enough that they would be thought of as weak that they would get fought. They knew that acquiescence would happen. And so they acted as if they were strong, not because they actually intended to fight, but rather because they wanted to act as if they were strong. In other words, this world of incomplete information, where there's bargaining involved, where there's competing preferences, where it's zero sum in a poker game, or where it's x and 1 minus x in a regular old ultimatum game, those worlds where it's bargaining, that provides incentive to misrepresent yourself, to behave as if you are strong, or to try to send the same signal that a strong person does. Not because you actually want to follow through on that, but rather because you know that you'll get a better deal that way. So there's intrigue not just across the two countries, but within a given country depending on what type it is. Now, this problem introduces yet another reason to want to focus on the role of international institutions. And it's with that in mind that I'd like to conclude with a provocative thought. So an advanced topic in game theory is, it's not even a topic in game theory so much as a part of, it's a related branch called mechanism design. And the idea of mechanism design is that it's like game theory but backwards. So in game theory, you write down a game. I've shown you so many games by now. You're so tired of games. You've seen games from Prisoner's Dilemma and Chicken and Assurance all the way through these relatively complicated extensive form games. We've seen repeated games that go on forever. We've seen ultimatum games with infinite strategy sets. We've seen so many different kinds of games. In game theory, what you do is you write down a game, one of many games, or maybe a new game that's never been written down before. You write down a game and you find its equilibria and you interpret them. Right? So here's the signaling game. Here's how you get the perfect Bayesian equilibrium. Let's interpret. Here's a deterrence game. Here's how you get the subgame perfect equilibrium. Interpret it. Here's a trade war game. Here's how you get the Bayesian-Nash equilibrium. Interpret it. Here's the prisoner's dilemma. Here's how you get the Nash equilibrium. Interpret it. So it goes game, solve, interpret. Game, solve, interpret. And you can interpret all sorts of different ways. You can interpret substantively, like, oh, well, war never happens in this model. You could interpret normatively, like this outcome is Pareto dominated. You could go any number of directions with how you interpret the results of an analysis, but it's always game, solve, interpret. Mechanism design puts that on its head. It says, tell me who the players are, and tell me what outcomes are possible and which ones you like. And heck, you can even tell me what information every given player has. So there are players, there are preferences, and there are information sets, information variables. But there is no game. There are no choices. There's no structure to the interaction to begin with. So there's nothing to solve, right? There's no equilibrium to think about yet. What we do in mechanism design is we take those basic building blocks and some desired outcome, and we say, okay, what game would I write down that would generate that desired outcome as an equilibrium? What institution would I design to generate the appropriate outcome? What constitution would I write down? What rules would I write down? What interactions would I write down? What strategies would I make available to which players? What would be the timing? Who would move first? Who would move second? Who would move 17th? Who moves when? Who does what? How does it all come together? What game would I write down to generate a given outcome that you told me you wanted to generate credibly, which is to say, as an equilibrium? So it's reverse game theory. Instead of game, solve, interpret, it's interpret, solve, game. And mechanism design, some of its most fruitful applications, and it was recently awarded a Nobel Prize, or some people that did this were awarded a Nobel Prize for their contributions to auction theory. So if you were an auction house and you wanted to figure out what rules of an auction you would set up, there's all sorts of different kinds of auction. Sometimes we bid sequentially, where there's an auctioneer going, no, 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 no. And I'm saying, I bet 5, and you're saying, I bet 10. It's sequential. I get to observe, right? Sometimes it's like you write down a bid and you put it in a jar. Sometimes it's sealed bid like that. And sometimes you pay what you bid, and sometimes you pay what the second highest bid was. And sometimes everybody has to pay. So there's many different rules. There's many different kinds of auctions we could have. There's many different games we could write down that are auctions. Now, all of them involve bidders, and all of them involve some product that we're trying to auction off, right? So we have players, we know what their information things are. Like, I know how much I value this bottle of water at. You know how much you value this bottle of water at. We don't know each other's valuation. So there's private information. The question is, what would be a good goal for our auction? And could we write down an auctioning system, an auctioning game that would generate that desired outcome as a Bayesian equilibrium? And the answer is it depends on what you're trying to do. So most auction houses are trying to maximize their revenue, right? They would like to come up with some auctioning mechanism that gets people to bid the most possible because they want to bring in a lot of money to the auction house. And it's not very hard to write down an institution that does that. Now, you can think about all the different things that you would do to make sure that that would be the case. You wouldn't want it to be an all-pay auction where you have to pay regardless of whether you won. If you made it be the case that you have to pay whether you win or lose the product, which is what happens in war, which is what happens in lobbying, if that were the case, then people wouldn't bid very much. And consequently, the person that liked the product the most wouldn't have to bid very much to win, and your auction house wouldn't make very much money. So you'd probably have it be that just the winner pays. And you wouldn't want them to be too concerned about bidding too much. So maybe you wouldn't have it be the first price. Maybe the second price is the one, right? So there'd be different rules. It'd probably be sequential because you'd want to make sure that people would have a chance to like psychologically riff on one another, right? So you design some institution, you set up an auction a certain way to try to maximize your revenues. So that's one goal you might have had. Another goal you might have had is, well, not only are we an auction house, but we're also an appraising firm. And part of our job is to figure out how much every product is worth. And we need good data for that. So I would like to set up a system that doesn't maximize revenues, but rather gets every bidder to truthfully reveal how much they value the product, irrespective of whether they get it or not. I want to come up with some scheme that incentivizes truthful revelation of private information. Auction houses try to do that too. And it turns out that the auction that you would have to maximize revenue is not the same as the auction you would have to truthfully reveal private information about how much you value the products. The reason I say this is, as soon as we see incomplete information game theory, and especially extensive form games with incomplete information, the number of equilibria, it gets to infinity real fast, okay? There's massive numbers of equilibria in games like this. That's why we don't try to find them all. There's so many equilibria that you almost have to stop and say, which equilibria are the interesting ones? Which equilibria are the bad ones? Which equilibria are the good ones? Where that could mean a lot of different things. It could be peace and war. It could be truthful revelation of information versus lying. It could be mediator builds trust and therefore creates peace versus mediator doesn't build trust. There's all sorts of different good and bad in terms of the outcomes. Now that again lives well outside of science. Which is a good outcome and which is a bad outcome? If you're an auction house, you don't need a scientist to tell you want to maximize revenues. So it's interesting, the further you get into game theory and using it to learn a lot about international relations, the harder you have to think about what a good equilibrium outcome would be. Now it's no longer just about here's a game and you solve it and you interpret it. Now it's here's an interaction that could go a lot of ways. If you could, what game would you write down? And why does that generate an outcome that you think is good? That's the institutional enterprise. I say these things because, there's a real opportunity for creative problem solving where we're looking for things that are robust. We want to find outcomes that are robust and stable, steady states. I don't want you to go out into the world and try to make some positive changes in international relations if that's what you wind up doing. I don't want you to go out into the world and try to make changes and try to change the world by incentivizing, by saying, you know what we're going to do? We're all going to pitch in this one thing, even though that's not an equilibrium. I don't want you to go out there naive. I only want you to say, I want equilibrium outcomes, but I don't want you to stop there. I also want you to say, I want good equilibrium outcomes. And you have to learn enough. You have to get deep enough into the theory. I have to teach you real hard. I have to show you a lot. And it's not because I want to torture you or anything. I don't get any pleasure out of that. But it's because if we don't sprint from the very beginning, if we don't sprint at week 1, if we don't sprint, then we don't get here. And if we don't get here, then I can't tell you the thing I'm trying to tell you right now, which is that this is just a giant canvas. The deeper you get, the less precise the answers become. The more things that could be equilibria if you construct them just right. But the more incentive there is for the players involved to lie to one another. So if you're going to go make change in the world, if you're going to go be a positive force, you have to understand, you have to have enough background to know you only want equilibria. And you have to have enough background to know that cheaters are going to cheat and liars are going to lie, and there's a lot of incentive to lie and to cheat, but that neither of those things preclude you from creating good outcomes, necessarily. And I hope that that's worth sprinting. I hope that these games and studying them, I hope that's fun too, but I hope that the larger lesson that rigor and good they can go together. Rigor and creativity can go together. Rigor and problem solving can go together. And I would argue, have to go together. We're not going to design good solutions to our international problems if we suddenly say, and then we'll get all the countries to want to love one another. It's anarchy. We have to be smart. Just a little food for thought as we begin to wrap up this class, because any given time you're slogging through a problem set, it might not be obvious just why you're doing it. And I hope that you see this as one very unified enterprise. Week 1 was part of this, and so was week 2, ... And so too will week 15. I'm looking forward to seeing you then. But in the meantime, thanks for watching.